Well, hello and welcome. In this video, I'll be covering section 1.3, which is over lines in the plane and the concept slope. My goal for you by the end of the video is to be able to use the slope-intercept form of a linear equation to sketch graphs, to be able to find slopes of lines passing through 2 points, to be able to use the point-slope form to write equations of lines, and to be able to find equations of both parallel and perpendicular lines. So let's first talk about a linear equation. So essentially a linear equation is anything that can be written in that form, y equals mx plus b, where m is representing the steepness or what we call the slope of the line, and b is representing the y-intercept. Anything in that format, y equals mx plus b, we can also call the slope-intercept form of the equation of a line. Now a line that's in the format of x equals a will always represent a vertical line, and technically that's the only type of line that cannot be represented in this slope-intercept form. It's also important to note that vertical lines are also the only types of lines that are not considered functions because they would fail the vertical line test. So let's go ahead and work through a few examples of this idea of graphing these linear equations. So when it comes to sketching graphs, my recommendation would be to first start with plotting a point and then just perform the slope repeatedly both directions, so to the right and to the left, and then just continue plotting points as you do that slope over and over until you have enough that you can connect and actually graph the line. I usually try and go as far left on the grid and as far right on the grid as I possibly can without going above or below whatever the end of that grid was. So if we look at this first example, notice we have y equals mx plus b format, so that means this 2 must be our m, or the slope, and the minus 1 or negative 1 would be our b value, or the y-intercept. So for this one, I'm going to go ahead and start at the one point that I should know, which is the y-intercept. Start at negative 1. And then from there, perform the slope both directions and just plot points as I go. So if I have a slope of 2, that means I have a rise of 2 places and a run of 1. So my next point would go right there. Another rise of 2 and a run of 1. Another rise of 2 and a run of 1. Then I can go back to my original point and then do the exact same thing but going to the left. Remember, a positive slope is going to be going up to the right, but I can also say down to the left, so I could say down to left 1, and then down to left 1 again. So that gave me as many points as I could fit on this grid, so I should be able to now just sketch a line that connects all of those points that I plotted. Now if we go to the next one, notice this one's in the format of just y equals 4, so technically I could say that this is also y equals 0x plus 4, to make it look more like slope-intercept form, which then means my slope is 0 and my y-intercept is 4. So if I plot that first point at 0, 4, or the y-intercept of 4, a slope of 0 implies that there's no rise, but as much run as I want. So it really is just a collection of all of these points that have the exact same y value, hence why the equation is just y equals 4. And notice that that created a perfectly horizontal line. We move on to the third one here, 2x plus 3y equals 3. What I might recommend with that is to go ahead and do a little side work and get it into slope-intercept form. So with this, I would go ahead and subtract the 2x first. So I'd get 3y is equal to negative 2x plus 3. And then go ahead and divide the 3 off of the y, so I now have y isolated. And if I divided one thing by 3, I divide everything by 3. So that gives me negative 2/3 x, and then plus 1. So it looks to me like my slope is negative 2/3, and my y-intercept is at 1. So I'll go ahead and start again, plot the first point I can do, which is the y-intercept, and now perform a slope of negative 2/3. So that would be down 2 and right 3. I'll do another down 2 and right 3 would take me right about there. I can then go back to my original point, go up 2, but this time left 3, so it's the perfect opposite. Do the same thing. And that gives me enough points that I should be able to now draw my line, throw the arrows on to imply it goes on forever. And now I've sketched the possible, graphs for each of these equations that I was presented with. All right, now moving on to the next concept, which is actually finding the slope of a line being given 2 points. So if I had 2 points provided to me, x1, y1, as well as x2, y2, x1, y1, and x2, y2, subscripts just representing which point it's from. To find the slope, again, slope, the words we can remember with this are rise over run. So notice I take the two y values and I subtract them in the numerator. So I find the difference of the y's, and then I divide it by the difference in the x values, making sure that I do in the exact same order from the second point to the first point, or technically you could switch it up and do the first point minus the second point. So technically we could also have this written as y1 minus y2. I just would need to make sure on the bottom I do x1 minus x2. So the order in which you subtract on top you need to be very mindful of, because you need to match that same order when you do the bottom. Now when the x and y axis have different units of measure, this concept of slope is actually oftentimes referred to as finding a rate or potentially a rate of change. So this idea of rate of change is going to be a concept that is going to be a pretty big phrase as we move forward. So just kind of connect as we're learning this concept of slope, that we also can call that a rate of change. Now some important things to note when you do these, I guess, formula-driven ideas of finding the slope. If you ever get y2 minus y1 equaling 0, that means 0 would be in the numerator. We actually just say that slope would be 0 at that point. If the x2 minus x1 equals 0, in other words, if the denominator was 0, then we actually use the word undefined to describe that slope. So hopefully that's something that you recall from the past. Horizontal lines always had a slope of 0. Vertical lines always had a slope that we called undefined. So let's do a few examples of actually finding slope between 2 points. I'll try and go through these relatively fast so as to not waste your time. But with this one, we have our 2 points provided. I'm going to go ahead and subtract the two y values. So I'll do negative 10 minus 2 on top. And I just need to make sure, since I chose negative 10 first on top, I need to make sure I choose 1 first on the bottom. So it's going to be 1, take away, and then negative 3. So that take away negative really is going to switch to addition. So I've got negative 12 in the numerator, and then 1 plus 3 on the bottom technically would turn into 4. And then negative 12 divided by 4 can reduce. So I'll go ahead and call that negative 3 because it can be simplified. If I move on to this second example here, if I do my slope again, I do my rise over run, so it'd be the y values subtracted on top over the x values in the same order. In this case, it really didn't matter because both of the y's were 5, so whether I was looking at that one first or this one first wouldn't have mattered. Looks like to me I chose this second one because I started with negative 2 on the bottom, but regardless, it's going to turn into 0 over, it really doesn't matter what that number is, because 0 divided by anything would just remain 0. So that one must be a horizontal line if I were to connect those two dots. If I go to the last one, do the exact same steps. My rise, so 3 minus 7 on top, over, and then 2 minus 2 on the bottom. I get negative 4 over 0. Well, I can't divide by 0, so with this one I actually just have to write out the word. This slope was undefined. And so now that we know how to find slopes, we can move on to another form of linear equations, which is called point-slope form. So if you're ever provided with a slope, so some value of m, and then some point x1 comma y1, the easiest way to actually come up with the linear equation for that is to actually plug straight into this thing called point-slope form. So what that looks like is, as you can see here in the middle of the screen, it's the y minus y1 being equivalent to the slope, or m, times, and then the grouping of x minus x1. So really, it's the m is going to turn into a number, the y1 will turn into a number, and x1 will turn into a number. I'll just substitute in, and notice I would leave the other letters x and y. That way it actually stays in the form of an equation. So let's go ahead and try an example here. If I said I want you to find the equation of a line that has a slope of negative 2, but it passes through this point 3, 5, I'd essentially just take each of those values. I'd do y minus the y1, so that should be the 5 from the point, being equal to my slope, negative 2, times in parentheses x minus the x value of the point they gave us, which was 3. Now normally we don't leave our answers in this format. Normally we go ahead and do the extra steps to actually get this into slope-intercept form. So what those steps would be to distribute through my slope to eliminate the parentheses on the right side, and then move whatever term was next to the y over to the other side. So since this one had a minus 5, I would just add 5 to move it over. So with this one, the equation in slope-intercept form would turn into, I'd have negative 2x, and if I distribute that negative 2 through, I'd end up with negative 2 times negative 3, which is positive 6, that I would add with that 5 to come up with a positive 11. So the equation of the line that passes through that point, 3, 5, and has the slope of negative 2, is this in slope-intercept form, y equals negative 2x plus 11. So just a quick summary thus far of what we've learned about the equations of lines. There are multiple names or forms of them. So if you want to pause and write these down, if you don't have these memorized, I would say go ahead and pause it now. But each one of these, you have the general form where notice it's essentially have all of your variables on one side, have it set equal to 0. And those a, b, and c values could just represent some possible integer or just a real number in all honesty. Vertical lines are ones that have the format x equals a number, so x equals a. Horizontal line would be like anything of the y equals format, so y equals b. Slope-intercept form was the first one we talked about, y equals mx plus b, and then point slope form, the y minus y1, being equal to the m, and then times in parentheses x minus x1. Now this general form at the very beginning here, sometimes books will reference that as standard form as well, so just kind of make them synonymous with each other. Standard form and general form for an equation of a line is this essentially where you have all of your variables on one side and have it set equal to 0. And now we'll talk about the last concept of the video, which is the concept of parallel lines as well as perpendicular lines. So parallel lines, by definition, are lines that won't intersect, and they will always have the same slope. So that would be another way of saying that the two slopes, if I were to set them equal, should be identical. It is important to note, though, that all vertical lines are considered parallel, even though we technically don't have a numerical value to set equal to each other. The fact that they are all undefined is why I know they would technically all still be parallel to one another. Now, perpendicular lines are essentially lines that form a right angle or a 90-degree angle and have slopes that are negative reciprocals of each other. Sometimes instead of saying negative reciprocals, you could also refer this as opposite reciprocals, because if you have one slope that's positive, the other one would have to be negative, and vice versa. If you had one slope that was negative, the other one would have to be positive in order for it to be perpendicular. Now, they do also have to be reciprocals, so remember reciprocals with, I guess, fractions. The easiest way to think of a reciprocal is essentially you're just flipping the numerator and denominator, or you're swapping them. So if you had something like 2/3, the perpendicular slope would be something like 3/2, but with a negative, because they have to be not only reciprocals, but they also have to be opposite. So if this was one slope, the slope perpendicular would equal that negative 3/2. So again, some notation for this. Parallel usually is going to be like 2 backslashes. Sometimes it could be 2 vertical lines. Those, anytime you see those symbols, that just implies that it's trying to shortcut saying the word parallel. Perpendicular usually is the one that looks like the upside down T to represent that it's forming a right angle. Now, with the idea of having negative reciprocals, the trickiest one with that is if you have a line with a slope of 0, the perpendicular slope of that we actually would call undefined. And it happens to work vice versa. If you know that the slope of one line was undefined, the perpendicular line then must also have a slope of 0. So we'll do one example that involves this idea of finding parallel or perpendicular lines. With this one, notice the instructions are telling us to just find the equations of lines that pass through a specific point. So this 3, -2, I'm going to use both times. And I want it to be parallel to this line one time, but then perpendicular to the same line the second time. So what can we do? Well, we could probably start getting what that slope is. If I subtract the 2x over to the other side, that gets me closer to having the slope-intercept form. When I divide by the -3, I don't know why I put it equals right there. That would have been plus. My apologies. But now, as we can see, our slope is going to be the combination of these two numbers that are in front of the x. So my slope for this, we know, is positive 2/3 because the two negatives would cancel out. So for the parallel one, I know that my slope is going to stay the same because parallel lines should have the same slope. May as well talk about the perpendicular one at this point. The slope of the perpendicular line is going to be the negative reciprocal of that fraction. So in this case, negative 3/2. So now that I have a slope and they provided a point, I should be able to use point slope form to come up with what this equation would be. So point slope form would look like y minus the y1, so that's really going to be like y plus 2, being equal to my slope 2/3 times, and then x minus the x1, which was 3. So if I go ahead and maybe get this into slope-intercept form, I could distribute through that 2/3 and then subtract the 2 over, and that would give me that y would equal 2/3 x. 2/3 times negative 3 would actually be a negative 2, and then minus another negative, or minus another 2, that would take me down to negative 4. So the equation of the line that's parallel to the given line and passed through this point 3, negative 2 is this y equals 2/3 x minus 4. Now if we go to the one that's perpendicular, we essentially start the same way, so it's still going to have the y plus 2 being equal to, but the only thing that's going to change is the slope now needs to be the negative or opposite reciprocal. Parenthesis inside, x minus 3 should remain the same because again we're still passing through that same point, 3 comma negative 2. So now if I distribute this one through, the numbers aren't quite as nice to deal with. I just do the same 2 steps, subtract the 2 over, distribute through, and I get this one would be y equals negative 3/2 x, a negative 3/2 times a negative 3, that actually turns into positive 9/2. And if I wanted to make it have a common denominator here, I could just multiply this by 2, so that would really be a positive 9/2 plus 4 more halves, which would give me a positive 13/2. So the equation of this line didn't have as nice of a y-intercept, but it still is something that I could plot and then perform the slope from if I needed to actually sketch it. Now if I wanted to practice just with one of these, just to show you, if I wanted to get that, what was called the general form, I'd essentially just start moving everything over to one side, and what is important to note with general form is we normally want to have the a term, or the term in front of the x, be positive and make sure that there's no fractions anywhere. So that is kind of the trickiest part, is how do I make sure it becomes positive and I get rid of all of the fractions. So I would first just subtract that x term over as well as add the constant term over, so that would turn into a negative 2/3 x. Then I'd have a plus y, and then I would have a plus 4 because I would have to add the 4 to move it over. Now I have my equals 0 on that side, but again, the fact that I have this negative 2/3 in front of that x, what I would do is essentially just distribute through a negative 3. And why would I choose to multiply by negative 3? Well, the negative gets rid of the negative in front, and then the 3 should cancel with the denominator that I have of 3. So if I actually distribute that through, and technically I would be multiplying the other side by negative 3 as well, but 0 times anything isn't going to change. So this now would turn into a positive 2x. A negative 3 times y would be a negative 3y. And a negative 3 times a positive 4 would be a negative 12. And that would equal 0. So that would be the first one, what it would be in that general form or standard form. And if you wanted to try it out on the second one on your own, by all means you could come up and I could check to see if you did it right. But anyway, I appreciate you guys taking the time to watch this video. As always, if you have questions, just let me know, and I will do everything I can to help you out. I guess I'll see you guys in class. Have a great rest of your day.